Some of the things we need is the following. Okay. So since it's documented, I can't deny it. It's been lousy exposition, but I hope I got the idea across on how we're proceeding and how the analog is to the MRA. And I mean, it sort of makes sense if you think about it to have these Q minus 1 guys. I mean, why Q minus 1? Why not 1,000 or whatever? But once you get past that hurdle, which is going to be explained a little more fully with what I'm about to say, then what we just did is a reasonable way to proceed. Mainly getting this orthogonal basis with W0, since we already have experience with that. It's just that we have more functions now. Possibly more functions. Okay, so in order to get at this number Q minus 1 of wavelets, there's a way of looking at it, and here it is. So in order to say it, I'm going to begin with this tiling level. And I think it's not unrealistic to just sketch some of these things, because the technology really, in a normal course when I do this, teaching 2 or 3 times a week, it takes a significant amount of time. But let Q be the vague measurable. Assume we have a covering of RD. Assume that the union, when lambda is in ZD, maybe I'll stop trying to be fancy with lattice and just use ZD, of lambda plus Q is equal to RD. The following are equivalent. Namely, for every lambda in ZD, excluding the origin, the measure of Q intersection lambda plus Q as measure 0. And that's equivalent to that the measure of Q is equal to 1. Now, in order to prove that, there are probably other ways of doing it, but one can prove it most neatly using the integral calculus. And basically, this reminds me of things that we did in harmonic analysis a long time ago related to work of Paul Cohen. But it's a type of technology that's been around and can be used to prove this. So proof. Let f, and I'm just going to sketch it. Let f of x be equal to the sum of as lambda is in ZD of the characteristic function of Q x minus lambda. So this is a lambda periodic function. I mean, it's a ZD periodic. This is ZD periodic. And the measure of Q, by by looking at intervals, can be evaluated. So the measure of Q, so and, the measure of Q is equal to, well, what is it? It's the integral of the characteristic function of Q over all of RD. And then we're just going to split that up to be the sum over all of our ZD of the integral 0, 1 d minus lambda of the characteristic function, right? And then making the change of variables, this just becomes equal to the sum lambda in ZD of the integral of the 0, 1 to the d of that translate but that's just f. So this is equal to the integral over all of 0, 1 to the d of f. Okay. And what is f? Because we have a covering, okay, because this is a covering, so we have this periodic and this, and f is bigger than or equal to 1 on RD. Okay, because of the covering hypothesis. And so we can conclude since, I'll write it down since I'm going to use the notation, since for every x in RD, we can find a lambda x in ZD such that x is in lambda x plus q. And so, therefore, take any x in RD, lambda q of x minus lambda x is equal to 1. And what does this say? This says, since that measure is equal to 0, also A, if and only if we have that f is equal to 1 almost everywhere. And so, there you go. Etc. So, there might be other ways of doing it, but this is sort of a neat way if you're running off. Now, using that tiling lemma, people who really thought about this most deeply, I think, were Gurkenig and Matic. And they wrote a paper that actually appeared in the IEEE in 1992, I believe. And I think it's one of those brilliant papers. I'm looking here to see if I have the actual 1992 in the IEEE. Because they combine analysis and counting arguments in sort of a brilliant way. So relevant and, by the way of thinking, great papers by Charlie Gurkenig and Wally Matic. then Yan Wang. And Jeff Legarius. And for this, IEEE 1992. And here, they've written a bunch of papers, but in the early years of my journal, just look in there and you'll see some of those articles referenced. And basically, this is one of the reasons that we expect to have Q wavelets for generating, including the scaling function, for generating all of, providing a wavelet orthonormal basis for V1 in terms of functions 1 in V0 and the rest in W0. So this is a theorem. And it says the number of cosets of A of ZD, where A is a dilation matrix, in ZD is Q equal to the determinant of it. Now that is a completely algebraic statement, obviously, and it can be proven by this analytic fact, uses the tiling limit. And I always think that one of the most amazing results in mathematics is the fundamental theorem of algebra, that every polynomial equation equals 0, say with complex coefficients, complex plane, has a root, and basically that's an algebraic fact, but there are no known proofs without using analysis or something equivalent to analysis using geometry. And so there may be some algebraic proof of that. I don't know, but I don't know.
The proof is as the same as the proof of fundamental algebra?
No. I didn't say that. That would be fascinating, of course, but I didn't say that. All I'm saying is, I don't know how to prove it just algebraically. The proof sort of requires some analysis. But, I mean, you're counting cosets, that should just be algebra. 1, 2, 3. To say that I don't know how to do it doesn't mean a lot of people.
I mean, just on the subject of that, the fundamental theorem, I mean, it kind of links algebra and analysis together, don't you think?
Oh, yeah, I do, actually.
As I say, I mean, how do you even define the complex numbers? You need analysis.
Okay, so you're absolutely right.
All right, never mind. I'm going. So it's a tangent. It's a tangent.
I was agreeing with you. I mean, it's. In fact, someone said something the other day, and they said it was. I think they said something of this nature of something being algebraic, but basically, I mean, they had to use the mean value theorem, and that goes right down to the definition of the real numbers. It's the least upper bound axioms. Okay. Well, what one does to prove the big theorem is one begins by doing the following. And I'm only going to sketch up to a point, state a result that's almost there, and then close with a couple of examples that I think are very revealing. So proposition so we're given the usual expansion of A and lambda, and a scaling function phi and a scaffolding dj, am I right? And let F be an L2 line, and RD. Then 1 over the determinant of A, the 1/2 F, is in V1, if and only if there exists an HF in the or an L2 of the torus. So now we're getting into sort of home ground here, right? For which the determinant of A is 1/2 F hat of the adjoint of A gamma is equal to H F of gamma, P hat of gamma, almost. Of course, this is exactly the situation we had when we were doing this simple dyadic case on R, but except now you do see how adjoints are going to arise where you didn't have them before, and that's it. And in this case, the L2 norm of H is equal to the same guy on that. And basically, let me explicitly use one of these change variable theorems since I did write them down. So proof. One over the determinant of A, the 1/2 F, belonging to V1 holds if and only if what? If and only if 1 over the determinant of A, the 1/2 F of A inverse of X belongs to V0, right? And therefore, we have that 1 over the determinant of A, the 1/2 F of A inverse X, we can write down, since it's in when it's in V0, it is H F of N in ZD, tau n phi of X in L2 of RD. And we know what the coefficient is, since these are orthonormal, where H F N is just the inner product of 1 over the determinant of A, the 1/2 F of A inverse X, tau n phi of X. Okay, so now if we take the Fourier transform of this thing, so just to show how this theorem plays a role here, taking the Fourier transform, so taking the Fourier transform, we have the following. We have that the determinant of A, the 1/2, now, because of the change of variable theorem way over there, we picked up an F hat of A star, the adjoint of gamma. And then I can pull out the phi there, I'll pick up an exponential, so I'll have the, is equal to phi hat of gamma times the sum h fn e to the minus 2 I n dot n z. Okay. And so I'm looking at the left-hand side here, and that does it. The norm comes out trivial, please. Now, it's not clear it's worth it, but basically, in fact, maybe I'll just say this. The fact that we had the number of cosets that we did plays a role, because what we end up doing is we end up looking at this function here, and we split it up into a sum of R functions, H, R, F of gamma, where R runs through the number of cosets. And it's, one shouldn't make apologies since I've done all the details, but but it's very technical, and you get the same answer. You get the answer of the theorem, and you get a way of building the wavelets. So I think on that score, I'm going to say, I mean, Strickhatz did it so beautifully. And besides Strickhatz is, by the way, Mayer's proof is wonderful. Mayer's did it first, and he did it in a fantastic way. And then he wrote a book on the matter. Dobushi has it. No, Dobushi doesn't have it in her book. But the Strickhatz article in the book I edited with Fraser is really superb. And then there's the book that's also very good by Wojtaszek.
Mm-hmm.
Now, I can get the first few letters here. And then write out C's and Z's. 5 or 6 of them. Maybe an S in there someplace. I don't know. It's Wojtaszek. And that's a very good book, by the way.
Is that the one that I had that I was looking
Yeah,
at?
that's the one you mentioned, yeah. And basically, in proving the theorem I'm going to state shortly, there's a big calculation. It's the major part of proof of the theorem I'm going to state shortly. And what one does is, so I know this sounds like I'm cheating, but it is quite technical, and I think I'll spare you that tonight. But the proof of the following theorem depends on the above as well as a complicated calculation of an inner product. But that's why going back to the idea is the critical thing. I mean, basically the idea is you expect, because of the number of cosets you have, That's a reasonable way of splitting things up. We do that here. That says that that's going to be maybe the right amount, the right number of elements for the number of wavelets in order to write down an orthonormal basis in the for V1. And in some sense, what you do after that, it looks very technical, but it sort of comes naturally, especially since we saw what to do with the dyadic wavelet, because we're building the same sorts of things here. We have the same sorts of relationships, and it's technical, but sort of clear. There are two stories that come to mind. This is a cop-out for actually doing a lot of technicalities here. There was a tremendous mathematical collaboration between Heidi and Littlewood, even when they weren't at the same university. And if you look at their work, it's extraordinarily technical. And someone said, how can you do such technical things? And one of the other said to the person who asked, well, we think about it so much that when the time comes to write it down, it looks technical, but it's actually rather easy. And the other story is sort of the flip side of that. A number of years ago, I was at Mittag Waveform Institute, and sort of the star there at the time was Anthony Selberg. All these other guys were there, including Paul Cohen, sort of Bombieri. They were loaded with really good people. But Selberg was the superstar there. And he talked about, and these were people working on the Riemann zeta function and the Riemann hypothesis. He was talking about work that Norman Levinson had done. Levinson had recently passed away. And Levinson had these articles, which again looked extraordinarily technical. And he was ending up proving that a certain percentage, like 1 or 2% of the zeros of the zeta function, the non-obvious ones, were in fact on the line and a half, where the Riemann hypothesis says they would be. But he was getting, it was like a small percentage. Other people have driven that up since then. A very small percentage. And Selberg said, Selberg would be a tough guy, Selberg said he felt that Levinson was very lucky because as opposed to the way Heidi and Littlewood thought, he said, well, Selberg, Levinson couldn't possibly have known what the answer was going to end up being. So it's an extraordinary remark by one of the really great mathematicians. Okay, so the main theorem, and I was copying out by not writing down all of the formulas, but I'm going to write down the main theorem and then go back and copy out some of the formulas, so at least you have a picture of the main theorem. So the main theorem is the one I began at the beginning. If you are given a dilation matrix and on a lattice, then if you take a multi-resolution corresponding to that, then you can come up with Q minus 1 wavelets and gives you a wavelet orthonormal basis. Okay, that is the theorem. Now, that doesn't say anything about smoothness or whatever. Then life gets rather even more complicated. But the theorem is, if you're in this lattice situation and you look at one of the myriad multi-resolution analyses that is inspired by that lattice, then there is a formula using functions like this function HF to make Q minus 1 wavelets. So those Q minus 1 guys are orthonormal basis for L2 lattice. That's the theorem. Okay? And as an intermediate step, let me just write down the notation and then I'll explain some of it. Is the following theorem. So the theorem given A lambda and a corresponding multi-resolution analysis phi bj. There exists q minus 1 constructible functions psi l, l equals 1 to q minus 1. The q is the determinant of A in W0 such that psi L M gamma is an orthonormal basis for L2 of R. Okay? That's the hard theorem I talked about a couple of classes ago. Okay? And then, to this end, in some sense straightforward, but definitely technical, to this end, we can prove the following. Same hypotheses, so theorem. Same hypotheses. Then part A translates by K of phi, where K is in ZD, is orthonormal if and only if. And now I'm going to write down some notation which I haven't defined, but I'll get back to that. If and only if the sum of these functions here, G0R of gamma squared is equal to Q almost everywhere, where R goes from 0 to Q minus 1. Now, since we know we're in an MRA, we know that this condition holds. So this is an alternative way of characterizing orthonormality. Okay? Now remember, this is going to be equivalent essentially to the way we had of doing orthonormality. Remember, we just in the real line, and we had a function phi on L2 of R, then we know that the translates of phi are orthonormal in L2 of R, if and only if the sum of the absolute value squared of phi hat of gamma plus n is equal to 1 almost everywhere. So this is this result here. The second part is tau n psi l, where n is in ZD. So I've same hypotheses and let psi 1 psi q minus 1 be functions in V1. Okay? So the tau n psi l, and we run from L is going to go from 0 up to some number p, which is going to be less than or equal to q minus 1, is orthonormal if and only if we look at these vectors, V, L, VP, sorry, gamma, are going to be vectors G0, P of gamma, G, I wrote P here, which is fine, L, 1 of gamma, up to GL Q minus 1 of gamma, where we're looking at L going from 0 up to P, are orthonormal in CQ, almost everything. And then we're actually going to get the basis issue, which goes back to that idea that I mentioned just before the break. And we're going to say that these guys here, tau n psi l, where n is in ZD, and P, L goes from 0, 1, up to Q minus 1, is an orthonormal basis for V1 if and only if the Q cross Q matrix U of gamma is G R L gamma is unitary almost everywhere. Okay, so the only thing one can hope for in a setting like this tonight on the planet Earth at this moment in time is to see the analog of the reasoning account. Basically, before the break, what I pointed out is we wanted to get an orthonormal basis for V1. I said, well, it sort of makes sense to look at Q of these guys because of something I was going to say after the break, which was this thing about counting the number of cosets. And then we had that condition on the coefficients, and that translated, which I didn't write down explicitly, into conditions on the corresponding trig series. And here, we're coming full circle around to what I wanted to talk about. I wanted to talk about functions, psi, being an orthonormal basis for V1, if and only if a certain matrix, and just like it was for the dyadic case on the real line with those trigonometric polynomials, except that now these are trigonometric polynomials on TG, we're going to get a Q by Q matrix being unitary. So it's very, very technical, and I'm copping out by not doing the technicalities, but this is an R here. And what I've done is, that's really going over the cosets, running over the cosets, where I split up the natural trig series like I did. There's a trig series, remember, H sub f, and I split it up, and I said, let's look at H sub FR. Let's look at H sub f is equal to the sum of the H sub FRs, and I'm just looking at integers over the various cosets. I don't want to say anything more. I said it all, basically, then, but to fill in the details is non-trivial. Okay, and then once you have this result, then, as William Moscone said when he saw our clear table, and even though there might be 10 balls in the table, but it was an open field that, you know, you lose, buddy, because it's straightforward to go from here. So that's the big picture given time constraints and whatever. Now, I do want to talk about some examples. The basically, one can do a lot here at several different levels. For example, 1, let's just take d equals 1, but when d is equal to 1, a is just going to be a number bigger than 1. And you can start writing things out for, I mean, just see what goes on when a is not an integer. I mean, how far can you go? But then if a is an integer, it's either 2, which we've already done, that's the case we've done, or 3, or 4. And life gets, it's rather interesting, even in this case, when you look at a not equal to 2. And there's 20 pages on that case. A case that I like, just because I think it has possibilities of tying in with coding theory, is to look at unitary matrices with primitive roots of unity. By the way, possibilities are just enormous here. I'm not going to mention everything, obviously.
Actually, one is one.
Huh?
The primitive things are big. Actually one is one, so it's not an item.
Oh no, but then you do things with it. I'm not telling you everything I know.
Do you mean like a 3x3 matrix with the 3?
I'm not going to talk about it.
Okay. Okay.
Wavelet theory on the torus. Wavelets on TD. So we know how to do that for tensor products, but we can do it in a more general case too. And this all broke open a long time ago, and now this is showing my ignorance because I haven't followed up on it. But this case here, so A, let's say A is in F. The disadvantage of this being televised, or recorded actually, televised, you have to read my lips, but I might be saying something, but absolutely no negative aspersions on anyone here. But if D is equal to 1 and A is bigger than 0, then there are two cases that arise that are not integers. We have A is P over Q, and B, we have A is not rational. And work was done on that. My recollection is, because I haven't followed it, is that some errors were found. But if I'm wrong, then what that person did is fine, and I'll be happy to tell you what I know about that at some point. Not tonight, though, but just come by my office, email me, whatever. But if there was an error there, I think this is a very interesting case. When A is not rational. And then there is the case of a very special case of looking, the case of looking at very special matrices. So 5 through 5 plus infinity. Then you'd start at 6 also. But this case here, let's look at. Let's ask what would a generalized Haar wavelet be in 2 dimensions? Well, one way to define it, there are several ways to do it. In fact, we've already done one. If you just take the dyadic one, we talked about that last time. One way of defining it would be to say that you would be choosing our functions h so that all the non-vanishing coefficients are equal. So in the Ha case, if you looked at the function h corresponding to the Ha wavelet, you've got the trigonometric series, which was all the coefficients were 0 except at the 0 spot and the 1 spot. They were both at the value, the same value, 1 over the square root of 2 or something. So that would be a reasonable way of defining a Ha matrix. So what we can do that with the dyadics, but can we do that with other matrices? Are there matrices just in 2 dimensions, so that when you look at that function h sub f that we talked about, that it's really just a trig function which has the property that all of its non-vanishing coefficients are equal. That's a possible definition. And basically that happens in the case of matrices like this. Where we're looking at Z2. And
So that leads to the unitary extension principle, that you can use that kind of matrices to generate frame wavelets.
now, I guess you know, I've worked in this problem with unitary extension. Maybe you don't, but I thought you might be talking about that. But I never thought of it in this context, so you could be right. But the stuff I did on it was give along the triangle, give a simpler proof of Warren-Chen's theorem. But this matrix, if you start off with this matrix and this lattice, then you can come up with a multi-resolution analysis corresponding to this with a function phi is going to be the characteristic function of a certain set. And that set is the following. I've got it right here on the table. Oh, if I blow this one, I did. That's the set, the twin dragon. And it's absolutely spectacular. This was a brilliant observation in this paper that I mentioned by Gurkin and Matic. So it's a fantastic paper. And also around the same time, I can think of Lawton, but he co-authored it with someone. I'm embarrassed to say I forgot who he co-authored it with. So it was in the air, so to speak. And so basically, for this simple looking matrix here, there is a scaling function and a scaffolding corresponding to this setup, giving rise to a multi-resolution analysis and therefore a wavelet theory, where the scaling function is the characteristic function of the twin dragon. Now that's truly a fractal set. And not only that, it's incestuous. I mean, basically, there are 2 twin dragons in there. And you can't see, they're not separated, are they? But anyhow, the wavelet is corresponding to that, is where you make the split here for the 2 dragons. It's 1 on one of the dragons and -1 on the other dragon. Now, another interesting fact about this innocent-looking matrix, what is its determinant? Its determinant is 2. So that is to say that even though we're in 2 dimensions, 1 wavelet will fill the bill. Okay? And this gets involved very much into non-separable filters and the like. So I mean, we're sort of ready to begin the subject now. One of the things that this does is, I mean, it generates very interesting lattices also. Because if you look at if you look at this lattice here, that's not Z2. That's the so-called quincunx lattice. And in any case, I mean, the quincunx lattice is sort of interesting. Basically, it the quincunx originally one of the traditional ways of thinking of the quincunx lattice. So this is out to 2 here. This is 1, 1. Etc. And one of the traditional ways of thinking of the quincunx lattice is because of statistics. Basically, I forgot what they call it, Galton's blocks or something, where it's a game you buy for your kids when you have kids. If you really want to distort and screw them up psychologically, you can tell, oh, and that's the normal distribution too. But basically, you have this box, and you drop little balls down a funnel, and they can bounce around different ways. Right? And they end up someplace, and you've got slots here for them, and it's going to end up like a normal distribution. But the lattice itself is a perfectly good lattice. It's a great lattice. And, huh? I didn't hear the key word you said.
Root system of B by B2.
Oh, so I didn't.
So
Root system.
yeah.
I don't know about that.
Can we do something about it?
Why don't you? That could be interesting. I never thought of it. Okay, so as I say, we've lots and lots of exciting things in this area, and so we gave a basic course, and wavelets when it began, people were a lot of people, and those who are still alive sort of deny it, but I do remember a lot of people saying this was going to be great with sliced bread. But it's a wonderful tool that's applicable for many situations, and it's not applicable for many situations. And I remember at the time, 15 years ago, people saying, oh, that's the end of the Gabola theory, but the Gabola theory is alive and well. Time frequency analysis is not going away. And people, like my own colleague Shia, have combined the Gabola theory with the wavelet theory. It's a very natural thing to do because underlying wavelet theory is the affine group, underlying the Gabola theory is the Heisenberg group. And to look at the non-abelian groups that interact that way. So mathematically, there's tremendous richness. And as far as applications go, even in our own Robert Wiener Center now, we're using the latest technology with shearlets and contourlets to study LiDAR data. It's a big area. It doesn't solve all problems, but it has a lot of applications. And that's the end of the course. And for
Now?
those of you who haven't passed me the homework, that's